So in this quick last section, we're going to summarize and point forward to what's going to happen next week. We've seen that overfitting is a really big problem. When we have too many degrees of freedom, or when we have too few data points to help inform the correct parameter setting for our model, we have overfitting. And we can think about what the cause of this is, right? The overfitting is caused by noise, and this noise can come from several different sources: stochastic noise, deterministic noise, as well as variance. Because the model can't differentiate noise from signal, it's just going to simply fit what's there in the data set, and that can lead to fitting the noise, which won't generalize to our test set. And in next week 6 lecture, we'll see two different cures to this disease. One is the idea of regularization, which is to say, even though we have an expressive model, maybe we can tune it down so it will only take on certain parameter values that we think are good. And secondly, an empirical solution, which is validation, which is something that we've touched upon already in class, where we look at the bottom line of the test cost to try to check whether the model is indeed overfitting, as we have done looking at some of these experiments where we know test cost. In summary, today we've looked at the bias variance trade-off, a very, very important concept that all machine learning students should be able to master. It deals with two different trade-offs. We have an impoverished model that has very little flexibility. We have problems with bias, being able to approximate F overall because our hypothesis space is too limited. On the other hand, when we have a hypothesis space that's pretty expressive and can capture the target function fairly well, we have problems in locating the actual good set of theta that's going to approximate that F, because there are simply too many things to choose from, and we'll be starting to fit the particularities of the training data. We want to make sure that we match the model complexity to the amount of data resources, both in quantity and quality, and not to the specific underlying target complexity, although that might be known to us. We can still certainly use that prior information when we do our modeling, but we have to really remember, because machine learning is a mathematical formalism, it will do whatever is optimal and won't by default take prior considerations into account. We've defined what we mean by overfitting, meaning that we fit the data more than is warranted. We've seen in several cases where the target function is better predicted with a lower order fit when we do not have enough data points. We've seen two causes for that, including the fitting of stochastic and deterministic noise. We'll add one more, which is the variance. And we've seen that the bias is really equivalent to deterministic noise because it doesn't change when we resample the data. This noise factor is really a quality of the hypothesis set's expressiveness. Great job! Now we have a good understanding of the trade-off in approximation and generalization, and we're going to look forward to next week's lecture on regularization and validation, which are our practical ways to solve this problem. We'll see you next week. Bye!